Assalamu alaikum everyone. I'm Abdul Halim Rahman, the second reporter of this group, and I'm going to discuss about phases 3 and 4 of systems development lifecycle, namely conceptual systems design and system evaluation and selection. Moving on to our topic, phase 3, conceptual systems design. The purpose of the conceptual design phase is to produce several alternative conceptual systems that satisfy the system requirements identified during systems analysis. By presenting users with a number of plausible alternatives, the systems professional avoids imposing preconceived constraints on the new system. The user will evaluate these conceptual models and settle on the alternatives that appear most plausible and appealing. These alternative designs then go to the system selection phase of systems development lifecycle, where their respective costs and benefits are compared and a single optimum design is chosen. By keeping systems design conceptual throughout these phases of the systems development lifecycle, we minimize the investment of resources in alternative designs that ultimately will be rejected. The conceptual system that emerges proceeds to the final phases of the systems development lifecycle, where it is designed in detail and implemented. This section describes two approaches to conceptual systems design. First, the structured approach, and then second, the object-oriented approach. The structured approach develops each new system from scratch from the top down. Object-oriented design, or OOD, builds systems from the bottom up through the assembly of reusable modules rather than create each system from scratch. So OOD, or object-oriented design, is most often associated with the iterative approach to systems development lifecycle, where small chunks or modules cycle through all of the SDLC phases rather rapidly with a short time frame from beginning to end. Then additional modules are added in some appropriate fashion until the whole system has been developed. So as we've said earlier, the structured design approach is a disciplined way of designing systems from the top down. And additionally, it consists of starting with the big picture of the proposed system that is gradually decomposed into more and more detail until it is fully understood. Under this approach, the business process under design is usually documented by data flow and structure diagrams. So as you can see here in this figure, it shows the use of data flow diagrams and a structure diagram to depict the top-down decomposition of a hypothetical business process. So we can see from these diagrams how the systems designer follows a top-down approach. The designer starts with an abstract description of the system, and then through successive steps, the designer redefines this view to produce a more detailed description. So in our example, process 2.0 in the context diagram is decomposed into an intermediate level data flow diagram. Process 2.3 in the intermediate data flow diagram is further decomposed into an elementary data flow diagram. This decomposition could involve several levels to obtain sufficient details. So let's assume that 3 levels are sufficient in this case. The final step transforms process 2.3.3 into a structure diagram that defines the program modules that will constitute the process. So the conceptual design phase should highlight the differences between critical features of competing systems rather than their similarities. Therefore, system designs at this point should be general. The designs should identify all the inputs, outputs, processes, and special features necessary to distinguish one alternative from another. In this figure, it presents two alternative conceptual designs for a purchasing system. These designs lack the details needed to implement the system. For instance, they do not include some necessary components, and by the way, we will talk about this later on, about these necessary components that are not included. Okay, so moving on. The designs do, however, possess sufficient detail to demonstrate how the two systems are conceptually different in their functions. To illustrate, let's examine the general features of each system. Okay, so option A. Option A is a traditional batch purchasing system. The initial input for the process is the purchase requisition from inventory control. When inventories reach their predetermined reorder points, new inventories are ordered according to their economic order quantity. Transmittal of purchase orders to suppliers takes place once a day via the US mail. In contrast, option B employs EDI technology, and then the trigger to this system is a purchase requisition from production planning. The purchases system determines the quantity and the vendor, and then transmits the order online via EDI software to the vendor. Both alternatives have pros and cons. A benefit of option A is its simplicity of design, ease of implementation, and lower demand for systems resources than option B. On one hand, a negative aspect of option A is that it requires the firm to carry inventories. On the other hand, option B may allow the firm to reduce or even eliminate inventories. This benefit comes at the cost of more expensive and sophisticated system resources. It is premature at this point to attempt to evaluate the relative merits of these alternatives. This is done formally in the next phase in the systems development life cycle. At this point, system designers are concerned only with identifying plausible system designs. Going back, these are the necessary components that are not included: database record structures, processing details, specific control techniques, formats for input screens and source documents, and then lastly, output report formats. Moving on to the other approach of the conceptual systems design, the object-oriented approach. This approach is to build information systems from reusable standard components or objects. Again, this approach may be equated to the process of building an automobile. Car manufacturers do not create each new model from scratch. New models are actually built from standard components that also go into other models. For example, each model of car produced by a particular manufacturer may use the same type of engine, gearbox, alternator, rear axle, radio, and so on. Some of the car's components will be industry standard products that are used by other manufacturers. Such things as wheels, tires, spark plugs, and headlights fall into this category. In fact, it may be that the only component actually created from scratch for a new car model is the body. The automobile industry operates in this fashion to stay competitive. By using standard components, car manufacturers minimize production and maintenance costs. At the same time, they can remain responsive to consumer demands for new products and preserve manufacturing flexibility by mixing and matching components according to the customer's specifications. The concept of reusability is central to the object-oriented approach to systems design. Once created, standard modules can be used in other systems with similar needs. Ideally, the organization systems professionals will create a library or an inventory of modules that can be used by other system designers within the firm. The benefits of this approach include reduced time and cost for development, maintenance, and testing, and improved user support and flexibility in the development process. Before we move on to the fourth phase of systems development lifecycle, we should know the auditor's role in conceptual systems design. The auditor is a stakeholder in all financial systems and thus has an interest in the conceptual design stage of the system. The auditability of a system depends in part on its design characteristics. Some computer auditing techniques require systems to be designed with special audit features that are integral to the system. These audit features must be specified at the conceptual design stage. Let's now move on to Phase 4, System Evaluation and Selection. The Systems Evaluation and Selection phase is an optimization process that seeks to identify the best system. This decision represents a critical juncture in the systems development lifecycle. At this point, there is a great deal of uncertainty about the system, and a poor decision here can be disastrous. The purpose of a formal evaluation and selection procedure is to structure this decision-making process and thereby reduce both uncertainty and the risk of making a poor decision. The evaluation and selection process involves two steps, namely, perform a detailed feasibility study and perform a cost-benefit analysis. The following discussion outlines 5 aspects of project feasibility that need to be considered. Each competing project will be assessed in the same manner. By assessing the major constraints on the proposed system, management can evaluate the project's likelihood for success before committing large amounts of financial and human resources. The acronym TELOS provides guidance for assessing project feasibility. The term stands for technical, economic, legal, operational, and schedule feasibility. So here are the 5 aspects of project feasibility. The first one is the technical feasibility. Technical feasibility is concerned with whether the system can be developed under existing technology or if new technology is needed. As a general proposition, the technology in the marketplace is far ahead of most firms' ability to apply it. Therefore, from an availability viewpoint, technical feasibility is not usually an issue. For most firms, The real issue is their desire and ability to apply available technology. Given that technology is the physical basis for most of the systems designs for most of the systems design features, this aspect bears heavily on the overall feasibility of the competing system. The second one is economic feasibility. This pertains to the availability of funds to complete the project. At this point, we are concerned with management's financial commitment to this project in view of other competing capital projects under consideration. The level of available economic support directly impacts the operational nature and scope of the proposed system. Later, a cost-benefit analysis is used to identify the best system design for the cost. The third one is legal feasibility. This identifies any conflicts between the conceptual system and the company's ability to discharge its legal responsibilities. In previous chapters, we have studied the need to comply with the control requirement laid down in the Sarbanes-Oxley Act and SAS 109. In addition, many regulations and statutes deal with invasion of privacy and the confidentiality of stored information. The decision maker must be certain the proposed system falls inside all legal boundaries. Second to the last, operational feasibility. This shows the degree of compatibility between the firm's existing procedures and personal skills and the operational requirements of the new system. Implementing the new system may require adopting new procedures and retraining operations personnel. The question that must be answered is, can adequate procedural changes be made, sufficient personnel restraint, and new skills obtained to make the system operationally feasible? Okay, and then lastly, schedule feasibility. Schedule feasibility relates to the firm's ability to implement the project within an acceptable time. This feasibility factor impacts both the scope of the project and whether it will be developed in-house or purchased from a software vendor. If the project as conceptually envisioned cannot be produced internally by the target date, then its design, its acquisition method, or the target date must be changed. The second step of Phase 4, perform a cost-benefit analysis. Cost-benefit analysis helps management determine whether the benefits received from a proposed system will outweigh its costs. This technique is frequently used for estimating the expected financial value of business investments. However, in this case, the investment is an information system, and the costs and benefits are more difficult to identify and quantify than those of traditional capital projects. Although imperfect for this setting, cost-benefit analysis is employed because of its simplicity and the absence of a clearly better alternative. In spite of its limitations, cost-benefit analysis combined with feasibility factors is a useful tool for comparing competing systems designs. Okay, so there are 3 steps in the application of cost-benefit analysis. The first one is identify costs. The second one is identify benefits. And then lastly, compare costs and benefits. The first step of the application of a cost-benefit analysis, identify costs. One method of identifying costs is to divide them into two categories: one-time costs and recurring costs. One-time costs include the initial investment to develop and implement the system. Recurring costs include operating and maintenance costs that recur over the life of the system. So as you can see in this table, it shows a breakdown of typical one-time and recurring costs. So under one-time costs, we have here hardware acquisition, site preparation, software acquisition, systems design, programming and testing, data conversion from old system to new system, and personnel training. And for recurring costs, we have hardware maintenance, software maintenance contracts, insurance, supplies, and personnel. The second step in the application of cost-benefit analysis is to identify the benefits of the system. These may be both tangible and intangible. So as you can see in this table, it lists several types of tangible benefits. So tangible benefits fall into two categories: those that increase revenue and those that reduce costs. For example, assume a proposed EDI system will allow the organization to reduce inventories and at the same time improve customer service by reducing stockouts. The reduction of inventories is a cost-reducing benefit. The proposed system will use fewer resources than the current system. The value of this benefit is a dollar amount of the carrying costs saved by the annual reduction in inventory. The estimated increase in sales due to better customer service is a revenue increasing benefit. When measuring cost savings, it is important to include only escapable costs in the analysis. Escapable costs are directly related to the system, and they cease to exist when the system ceases to exist. Some costs that appear to be escapable to the user are not truly escapable, and if included, can lead to a flawed analysis. For example, data processing centers often charge back their operating costs to their user constituency through cost allocations. The chargeback rate they use for this application includes both fixed costs and direct costs created by the activities of individual users. So we have here examples of increased revenues in this table. Under increased revenues, increased sales within existing markets, and expansion into other markets. As for cost reduction, labor reduction, operating cost reduction, reduced inventories, less expensive equipment, and lastly, reduced equipment maintenance. In this figure, it illustrates the technique that has been said. Okay, so let's assume the management in user area B proposes to acquire a computer system and perform its own data processing locally. One benefit of the proposal is the cost savings derived by escaping the chargeback from the current data processing center. Although the user may see this as a $400,000 annual charge, Only the direct cost portion is escapable by the organization as a whole. Should the proposal be approved, the remaining $350,000 of the chargeback does not go away. The remaining users of the current system must now absorb this cost. So in this table, we have here a list of some common categories of intangible benefits. Although intangible benefits are often of overriding importance in information system decisions, they cannot be easily measured and quantified. For example, assume that a proposed point of sale system for a department store will reduce the average time to process a customer sales transaction from 11 minutes to 3 minutes. The time saved can be quantified and produces a tangible benefit in the form of an operating cost saving. An intangible asset is improved customer satisfaction. No one likes to stand in a long line to pay for purchases. Okay, so there have it, the list of intangible benefits: increased customer satisfaction, improved employee satisfaction, more current information, improved decision making, faster response to competitor actions, more efficient operations, better internal and external communications, improved planning, operational flexibility, and improved control environment. Okay, now the third and the last step in applying the cost-benefit analysis is to compare the costs and benefits identified in the first two steps. The two most common methods used for evaluating information systems are net present value and payback. So under the net present value method, the present value of the costs is deducted from the present value of the benefits over the life of the system. Projects with a positive net present value are economically feasible. When comparing competing projects, the optimal choice is the project with the greatest net present value. Okay, so in this table, it illustrates the net present value method by comparing two competing designs. So if costs and tangible benefits alone were being considered, then design A would be selected over design B. However, the value of intangible benefits along with the design feasibility scores must also be factored into the final analysis. The payback method is a variation of break-even analysis. The break-even point is reached when total costs equal total benefits. As you can see here in these two figures, they illustrate the approach using the data from the previous example. The total cost curve consists of the one-time costs plus the present value of the recurring costs over the life of the project. The total benefits curve is the present value of the tangible benefits. The interaction of these lines represents the number of years into the future when the project breaks even or pays for itself. The shaded area between the benefit curve and the total cost curve represents the present value of future profits earned by the system. In choosing an information system, payback Speed is often a decisive factor. With brief product life cycles and rapid advances in technology, the effective lives of information systems tend to be short. Using this criterion, Design B with a payback period of 4 years would be selected over Design A, whose payback will take 4.5 years. The length of the payback period often takes precedence over the considerations represented by intangible benefits. Moving on, prepare systems selection report. The deliverable product of the systems selection process is the systems selection report. This formal document consists of a revised feasibility study, a cost-benefit analysis, and a list and explanation of intangible benefits for each alternative design. On the basis of this report, the steering committee will select a single system that will go forward to the next phase of the system's development lifecycle, detailed design. So as for the last part of phase 4, we should know the auditor's role in evaluation and selection. The primary concern for auditors is that the economic feasibility of the proposed system is measured as accurately as possible. Specifically, the auditor should ensure these 5 things. First, only escapable costs are used in calculation of cost savings benefits. Second, reasonable interest rates are used in measuring present values of cash flows. Third, one-time and recurring costs are completely and accurately reported. It should be accurately reported. For the fourth one is realistic, useful lives are used in comparing competing projects. And then lastly, intangible benefits are assigned reasonable financial values. Another thing is that errors, omissions, and misrepresentations in the accounting for such items can distort the analysis and may result in a materially flawed decision.